Hello and welcome to Easy Projects. So in this video we'll start looking at what FPGAs are, what they can be used for, and how we get them to do what we want. So FPGA is an acronym for Field-programmable Gate Array. So the FPGA is a whole bunch of logic elements which we can use to do practically everything we want with digital electronics. We cannot do anything analog. That is with the FPGA core itself, because some FPGAs do have built-in analog to digital converters. There is different ways of telling the FPGA what you want the logic elements inside to do. We will be using VHDL, which is an acronym for Very High Speed Hardware Description Language. And as the name implies, it's a language that describes hardware. There's other languages like Verilog, but we won't be looking into that. You can also get some programs where you can draw schematics instead of writing code, but they are usually a lot more limited in what you can do. So let's take a look at the FPGA itself, and then we can come back to the VHDL part when we have looked at the FPGA. If we imagine the FPGA chip as this black box, we of course have some input pins. And they're not distributed very evenly, but you get the point. It could be along the edge like this, like a quad flat pack package, or it could be as round pads underneath, like a BGA package. Inside the FPGA we have an array of these logic elements, and I'll just draw a few, but there can be hundreds of thousands of these inside an FPGA. The development board that I have 115,000 logic elements, but you can also get them down to a few thousand. It depends on what you need to build, how big an FPGA you need, of course. Just when you choose a processor or microcontroller. Speaking of microcontrollers, inside an FPGA everything runs in parallel, and you might know that a microprocessor does everything synchronously. So it will run one line of code after the other, and if you have too much code, then it takes quite some time for it before it starts over and you can run the first part of the code again. An FPGA doesn't work like that because there's no program inside an FPGA. It's just hardware blocks. So you can configure this part of the FPGA, for example, independently of this part, almost like they were two separate chips, and everything will run in parallel. You could even use every single logic element independently, but of course there would not be enough input and output pins for that, so you could not utilize all the logic elements that way. And typically that's not what you do, because then you would just buy some logic chips and put into your board. Usually these logic elements have a number of inputs. Let's say I'll draw 4 here. It varies a lot how many inputs there are. They can be from 2 to 6 or 8. I don't know the exact numbers, but it varies a lot. But usually there will be 1 or 2 outputs, and let's just stick with 1. If there's 2, it's usually because this can be divided up, so we can use some of the inputs for one output and the others for another output, but let's not go there. So you can think of the logic element as a big truth table. So now I only made 3 inputs here, and we have 1 output, and over here we have 4. Just ignore the last one. You could configure this logic element in any way you want. So you could choose that you want the output to be high when only the first pin is high. That would be, let's say, this one. And also when the last one is high, that would be this one. And when all of them is high. And the rest you want it to be 0. You could then connect these pins to the input pins. And you could connect the output to another pin. Now, when any one of these three input patterns is on these three pins, we will get a high here, otherwise we'll get a 0. You can see this is only using one logic element and 4 pins, so it's not a very efficient operation, but you might need something like that. But instead of having this pin going to an output, we could have made it go to the input of another one, and this one could come from down there, and so on. So we can interconnect all these logic elements, and that way we can make very complicated hardware. So as you can see, everything here works exactly as discrete logic chips. We could even draw this as logic chips if we wanted. The output is either one of these three combinations, so that would be an OR gate. And these conditions would be AND gates. So the top pin of these would be input A, the middle would be B, and the lower one would be C. So for the first one, we will need a high on the C. So that's this one. And the other two should be low, so we will invert those with an inverter. Just meaning that when these are low and this one is high, the output will be high. The next one, it's only the first one. And the last one, we need all three. So you could build this same circuit up using discrete logic this way, with some inverters, some AND gates, and an OR gate. Okay, so everything is happening in parallel and at the same time. But you might not always want that. If you want to send some data, then you need some kind of a clock to reference it all to, and you need a sequence to send the data. You cannot just send everything at the same time. So there's also inside each of these logic elements a flip-flop. It might not be a D flip-flop, I'm not really sure about that, but I would guess it would be a D. So we could connect a clock signal to the clock pin of the flip-flop. And then whenever we have a rising edge on the clock, it would take whatever is on the D pin and put that on the Q pin, and the opposite on the Q naught. So this way we can reference everything to a clock signal, and by cascading the flip-flops in series, we can make counters and stuff like that. And by putting them in, like parallel, we can make registers. So there's two more things I want to mention before we move on to the VHDL. One is that the pins are not connected directly to the logic elements. There is something called I/O blocks in between. Usually the core of the FPGA runs on a low voltage. I'm not sure, but I think it's around 1.2 to 1.8 volts. And usually everything you need to connect to runs on a higher voltage, like 5 volts or 3.3 volts, 2.5 volts, or it could also be 1.8. I'm not sure if you can get 5 volt I/O for any FPGAs, but at least they can go up to 3.3 volts. So you can power one I/O block from 3.3 volts, for example, and then you can power another one from, say, 2.5 volts. So depending on what you need to connect to, you can use different voltages on different I/O blocks. You also need to be careful, of course, when you have different voltages, that you connect the right stuff to the right pins. So we could make this one 3.3 as well. and then we don't care about the last one. So the standard way inputs and outputs work, and you will also know that from microcontrollers, is that you have a single pin. You can define it as an output, or you can define it as an input. If it's an input, it will have a lower limit and a higher limit. If you're below the lower limit, you will know that your input is a 0, and if you're above the high limit, you will know that it's a 1. If you're in between here, you don't really know what to expect, but usually kind of in the middle is where it changes over. But for a good design, you want to be below the low limit for a 0 and above the high for a 1. If you get up to very high speed signals, and say this is 3.3 volts, the output of the transmitting end has to swing quite a lot. And if you have inductance and capacitance on the way, a perfectly fine square wave on the output of something might not be perfectly square wave when it reaches the other end. So usually the lower your signal is, the less it has to move. But lowering the voltage won't help with the noise, of course. So most FPGAs will also do differential inputs and outputs, where you don't use one pin, but 2 pins for each input and output. And the differential doesn't really look at the voltage. It looks at the difference of the 2 pins. So if you have one voltage there, and it then does that, and you have the other voltage here, and it does that, then it will look and see that this pin is higher than this one. That could represent a 1. And here they change. So the other one is now higher than this one. And that would then mean a 0. You can see here, first of all, we get double the slew rate because both pins are changing. And also the voltage difference between these two can be very little. The second thing is that the differential signal is also very good at suppressing noise, because usually you have these 2 tracks running right next to each other on the PCB. And since they're not really evaluated with respect to ground, but only with respect to each other, then if you introduce noise to one signal, say there's a little bump there, and this is extremely exaggerated, but it's so you get the idea. You can see here we're very close to the red line, but since the tracks run right next to each other, the same noise would appear on the red line, and the signals are actually equally spaced, even though we have the noise. If we do the same thing on a ground reference signal, then the ground is always a solid 0 volts, because that's where we take our reference. So if we introduce any noise to one of the tracks, then we will get this bump in the voltage. And if this is very close to the limit, then it will think it's a 1 now, when it should have still been a 0. We are not really going to use this in this series anytime soon, but I'm just saying that it's an option if you need it. Most FPGAs will do this. But for now we'll just stick with the regular ground referenced single-ended input and outputs. The last thing I want to mention is that we can have one or more phase lock loops inside an FPGA. You could of course always divide the clock down using the flip-flops, and then maybe you could divide the clock signal by 16, and you could use that for some other part of the FPGA's logic. If you need to send data over UART, or you need to send it to a character LCD display, you might not want 100 or 50 megahertz of data going to that. You could use the flip-flops to divide down the clock, but that would take hardware, and you can really only get the division in powers of 2 of the main clock, unless you don't care about the propagation delay. You can set up a chain of flip-flops and then run them synchronously with the clock. And you can get your half output, a quarter, 1/8, 1/16, and so on. And that will only give you the propagation delay of 1 of the flip-flops. But if you start adding gates to these signals and you feed that to another chain of flip-flops and so on to get your desired frequency, then your final clock output will be shifted in phase compared to the main clock. And you don't really want that inside an FPGA, because if you do that a lot, you might end up having more than one clock period of propagation delay, and then nothing will work. You can get around that using the PLL, and we will be using that in this project also. So the PLL will take the main clock, and the internal circuitry will do exactly as the name suggests. It will lock the output to the phase of the input. So whatever you divide the output down to, it will always make sure that the rising edge lines up with the rising edge on the input clock. This of course means that there must be an integer division between these two for it to happen. I don't think we're going to look at exactly how this works internally, but we just want to know that it is there and we can use it. So if you, for example, want to divide the input clock by 37, it would probably be better to use the PLA than to make it in hardware. If you were to divide it by 8, it wouldn't really matter that much. And by the way, I'm not saying that it will not work if you're doing it in hardware, because there is a lot of headroom, and depending on your clock speed, of course, it can be more or less. The slower the clock you're running, the more headroom you'll have, of course, before you start to get into problems. So there's probably still something that I forgot, and if there is, then we will get back to it later. Now we will go on and take a look at the VHDL. And by the way, if you want to dig deeper into FPGAs and you want some prettier drawings, then check out EEVblog's videos on the topic. I can remember at least 2 that he made. One is called What's an FPGA, and the other one is Microcontrollers versus FPGAs. They are very good videos and they are definitely worth a watch. I'll put the links down below. Okay, so VHDL is the language that we'll be using to describe the hardware inside the FPGA. When talking about VHDL, there's 2 keywords. One is entity, and the other one is architecture. And as I described in the previous video, if we think of our code as different blocks that we link together, then the perimeter of these blocks, so the inputs and outputs, and if we have some constants that we will define, that will be the entity. So we can say we make 2 inputs and we have 1 output. This will in short terms be our entity. The architecture is all the logic that is inside the entity. And we don't want to dig too deep, but there can be more architectures inside an entity, but we don't really want to do that. Or at least I haven't come across any reason to do it. So you could have, for example, an AND gate. Now let's make it 3 inputs instead. And then an OR gate. Then the architecture could be something like this. Oops, I didn't mean to do that. So this is just an example. You would, of course, have more stuff in there. We could make another one. Okay, so I just made another one here. and it's a 4-bit counter. It's not very pretty, but it's to give the idea that we can make some circuitry control the enable input of this counter, and then we can feed the clock directly to it, and then we can get a count output. We would put these in 2 different blocks, or 2 different entities. And then to implement it, we would have one big entity where these 2 entities will be part of this architecture. Or basically the architecture of the top level entity will use these 2 blocks for its hardware. It will be a lot easier to understand when we get to write the code, because we don't really have to think about how all this is made. So let's go and take a look at the code so I don't confuse you more than I have to. So we go into the Quartus Prime software, and we already made a project in the last video, so we can open that. Projects, big clock, and I found my files tab. It's just up here now. So in the last video I just wrote some text here so we could save the file, and actually we need something first. We need to tell it that we use a library called IEEE, and that's with the library keyword. And then you use semicolon to terminate a line like you do in C or C#, C++. And by the way, VHDL is not case sensitive, so you could do that, would mean the same, or this. It doesn't give a flying anything about that. I usually use capital letters for signals and normal letters for everything else. So we need to tell it that we want to use from the IEEE. It's called std logic. Underscore 1164.all. We will need this to create signals, so we basically always want to use it. So now we can create our entity, and we simply type entity, and then we give it a name. You can call it whatever you want. And then it should be followed by is. Then to define the inputs and outputs, we will have to use the port keyword. And we'll make a parenthesis. We know we will need a clock input. And it should be an input, so we make a name followed by a colon and then the direction, so it should be in. And it should be standard logic. Then we terminate it with a semicolon. And the next line, we don't really know what we want yet, but if we were making a count or something, we would need, say, an output. And that would be an out. And now if we wanted like a count output, it would probably have more bits, like it would have one for ones, for twos, for fours and eights, and so on, depending on how many bits we get. So instead of just standard logic, we can make it a standard logic vector. Then we need to specify the number of bits. So we'll start by the most significant and say we want a 4-bit counter, and we'll make the most significant bit number 3. Then we write down to in one word, if I can spell, and then 0. So 0 will be the lowest bit. This will create a vector where the leftmost bit is the most significant bit, and the rightmost will be the least significant bit, like when you do C programming and stuff like that. You could also do it the other way around. So you could write 3 to 1. That will flip the order. So the left bit would be the least significant and the top one would be the most significant. It can be an easy way to reverse data if you need to, but I usually make them down to, because I think it's easier to work with. Now, if this was our last piece of I/O, we would not make a semicolon. We would make the end parentheses and then the semicolon. So we end this one and say we're done for now. We will write end and then the name again. And I cannot hit the correct keys. So I'll just make a few more inputs and outputs. So we have something very easy to work with in our architecture. To make the architecture, we type the keyword architecture. And then we give it a name. A lot of people call it behavioral or something like that, but that's a long word. I usually just call it arc, like that. But it doesn't really matter as long as you know what it is. Then you write off, and then the architecture that it is part of. And then is. And if we want to define any signals, we can do that here. They will be local to the architecture and cannot be seen outside the block if you want. The port I/O that we define up here can only be an input if it's set to an input, and only an output if it's set to an output. That can never be changed. You can define them as in-out or buffers, but that can get really messy really fast, so only do that if you have to. So for now we don't really want to define any signals, so we just type begin. And you have to define your signals between architecture and begin. Then we might as well just type the end keyword before we forget, and then the name of the architecture. So between begin and end is where all our hardware should be. And let's start with the most simple one. If you want to route a signal directly from an input to an output, you can type the output, then make an arrow with a less than sign and an equal sign, and then type the input that you want to route, or a local signal or whatever. So this means that Q is always connected to A. And that really means always. If you change it somewhere down here, say that Q is connected to B, then you would make a direct short between A and B, and the program will not allow you to do that. Then you would have to use something like a when statement. Then you could write else. Oops, let's take it there. B when C equals 0. So this will be called a signal assignment. And you can check your syntax if you run the analysis and synthesis. And it tells me that I screwed up because I can't spell. So that's better. So it accepted this, so I probably didn't make any errors. We probably get some warnings because we don't use half of the inputs and outputs that we defined up here. And if we wanted to make a signal in here, we could also do that. We use the signal keyword, then we need a name. Could be something. And we make the colon. And we don't need to specify if it's an input or an output. It's just a general purpose signal that we can use for anything. But we do need to type the type of signal. And I need to do this correctly. And then a semicolon. And it's a good idea to give these a value, and you can do that by typing colon equals, and then, for example, 0. We can also compare things and make synchronous logic if we make a process. And to do that, we use the process keyword. Then we make parentheses, and inside here we have what's called a sensitivity list. You put names of signals and inputs in here to tell the program what the process should be looking for. The process will run whenever something happens to one of these signals. So you could say in this case we only want to look at clock. And then somebody puts is here. It works with it and it works without it. And so I'm just recording this part again because the NVIDIA Shadowplay software that I used to record it chose to crap out for some reason, and I lost 20 minutes of footage. But anyway, you don't have to put this is. If somebody knows if it has a use, you're of course welcome to mention that in the comments. I haven't looked into it, I've just seen people use it and other people don't use it. A process needs to begin with a begin keyword. And we might as well make the end at the same time. And it has to be end process. As I said earlier, we can compare things inside a process and make synchronous logic. So we can use the if statement. And since this is sensitive to clock, we want to check if we get a rising edge clock. So we write rising edge and CLK in parentheses. And then we have to use the then keyword. And then if we want to make a binary counter, we want to count the output up every time there is a rising edge on the clock. And by the way, if we don't use this rising edge, but we instead write if clock is equal to 1, then what's inside the if statement will run as long as the clock is equal to 1. So if it's a counter, it will count full speed as long as the clock is equal to 1, and when the clock is then 0, it will stop counting, and then when it gets 1 again, it will count full speed. If you want only a single increment, then we need the rising edge clock. And then we can end if. And to count up the output, we might be tempted to do something like this. And then our arrow. And we can do this +1 because it's a vector. Then the VHDL will automatically increment it and wrap it around to 0 when it reaches 1, 1, 1, 1. But we have a problem here because we specified output should be an output, and here we're trying to read the value and add 1. We cannot do that. So to solve it, we need to make a new signal. We'll call it countout. And we will make it a standard logic vector, just like this one. and we will initialize it to all zeros. You saw me use this before, and if it's a logic vector, we can set each bit, and we can also set, we can do this, others, and then we actually need to reverse the arrow compared to what we used to, and then write 0. So what this will do is it will set the bits that we specify here, and then all the others will be 0. In this case, we didn't specify any, so it will set all the bits to 0. And by the way, I went and removed the other signal that we created because we weren't using it. And as I said, I lost the footage, so I'm retaking this. Also, I said that we're using the standard logic unsigned.all part of the EEE. We need this when we do when we increment signals. I forgot to mention that. So we created our signal, and we can now use this name instead. Now this is legal because we can both read and write to this signal. But we of course need to route this signal to our output signal, and we do that like this. So output is always connected to countout. And let's run our analysis and synthesis. Let's just save the file. See if I did something stupid. And I didn't. So with the if statement here, let's just copy it. The condition here, you can put any logic expression that you want. So we could go if, for example, if A and B or C, then this would happen. Now this doesn't make any sense, but you would put some other code in here. Then it will look at this. If A and B are high or C, then this code will run. And these two if statements will run in parallel. It will not do this one before this one. They will happen at the same time. All the code you have in the process will happen at the same time. So if you have, say, 4 if statements, then as soon as the process begins, all these will start at the same time. Let's get rid of this. Also, you can do something out here. You can say Q should be A and B. So this is not legal when I do this, but if I remove this, then we can do this. 2 dashes will be a comment. So this should still work. So that would be a AND gate. You could also make it or you could make longer expressions like this, A or B and C, for example. But we will get back to all this in a later video. We'll also look further into all the different signal assignments and if statements, and we have case statements and all that kind of stuff. I think this will be it for the code in this video. And now we'll take a look at how we can put this onto the FPGA development board, so we can see that it indeed works. So this will probably work just fine, but we have a slight problem down here. It's not actually a problem, it will run just as we desire, but visually there will be some problems. So the first thing we need to do before we can put it onto the board is to assign the inputs and outputs to the pins on the FPGA. And This is very easy. We just go up here to the pin planner. We open that. And now all the numbers are already plugged in because, as I said, I have already recorded this once, but I lost the footage. So what we do is we go to the internet and we find the pin assignment for this development board. This is from script.com, and there also comes one with the development board, of course, but I don't have the CD right here. So the inputs, the A, B, and C, we want to use the slide switches, and these are here. We can see the pin numbers here. It's pin underscore AB28 and then AC28 and AC27. We remember these numbers and then we go to the Quartus software and then we put them in at this. We can see the IO standard is 2.5 volts and that also corresponds to what we find in here. No, it actually depends on JP7. But for the LEDs, it's 2.5 volts, and that is also set here. And JP7 is set to 2.5 volts. So this will be correct. You can also take one of these node names and drag it onto a pin and assign it that way. But I find it much faster just to type in the names, because else you'll have to go right A, B, that's there, and then you have to go to 28, that's all the way over there, and then you can drag it there. It's much easier just to type in the names. You can also specify how much current you will allow on the outputs, but we won't be doing that right now. The default 8 milliamps will be just fine. The next signal is the clock. Then we need to find the clock oscillator and see which pin that is connected to. I know that already, and you also saw it, but we can go here to the clock inputs. We have 3 clock inputs on this development board, and here are the pins. We'll be using the first one, which is Y2. And we put that in here. Now the outputs, we would like red LEDs for the count outputs, and then the Q output, which is our gate output, we would want a green LED. So we go again, you probably guessed it, to the pin assignment table here, and we find the green LED is right here. We remember that number. And then the red LEDs, we use those for. And we just put the numbers in. And if you have inputs or outputs here that you do not specify a pin, then you can see this fit allocation. It will choose a random one for you, and you probably don't want that. So just make sure to fill them all in. When we have done that, we can click the X, and we can go back to our code. Now we run the full synthesis, analysis and synthesis, the FETA assembler. That will generate our programming files. We can also run a time quest that will make a timing analysis and determine if our clock speed is too fast for our propagation delays, and it will not be in this case, but we haven't set it up, so it cannot check it anyway. We want to run this, and depending on your design, this can take quite some time. Now it won't take very long because we only have like 10 lines of actual code. But if you have pages upon pages, then it can take a few minutes. And if you have very large projects, if you are almost filling the FPGA, I've never tried that myself, but I think it could go upwards to 20 minutes or something, depending on your processor, of course. So we have 7 warnings here, and you can see most of them will be in the time quest timing analysis. And again, that's because we haven't set it up. we can see it have generated our programming file, and we can now open the program device to program it. You don't have to add a device. Actually, I made this mistake the first time. You just add a file, go to output files, and you double click it, and then we have it. It might say no hardware up here the first time, and if it does, then it's just because the driver had not been installed when you installed the Quartus. Then you can go into where the Quartus is installed. There will be a folder called drivers, and you can install the driver from there. Else it should show up in the hardware setup as USB Blaster. For some reason it didn't install the driver. I thought it did when it ran the Quartus installation, but I found the driver in the Quartus installation folder, so I could just install it afterwards. We select the USB Blaster, and then we can program the chip by pressing start. And I'll just switch to the camera so we can see the board, and then we'll press start. We put the USB cable into the USB Blaster input, and then we turn it on, and there's this standard program on the board. And what we're doing is actually just reprogramming the FPGA. We're not putting the program onto the flash memory just yet. We'll do that later. So if you happen to have the same board as me, there's this little switch where it says run and program, and this has to be on run because that's very intuitive, but it has when we're doing it like this. And then we go to the computer and we just press the start. So I just hit the start button, and it should, no, it shouldn't. I don't know what happened there, but it seems like it's working now. And our switches are these switches. And basically it was like, if we look at the code, then our A input is this one, B is this one, and C is this one. So C determines if the LED should be routed to this or this switch. So if it's down, it should be this, it should be this one. And if it is up, it should be this one. Then now we can see I can switch it to this one, and nothing happens here. And if I do it the other way, then this one controls the LED. I hope it lights up on the camera. But you might be able to see our problem here. Our counter doesn't seem to work. But actually it is working, it's just this LED is flashing at 25 megahertz. And the next one is 12.5 and 625 and so on. So we need to do something about that. And the easiest way for now is just to extend the counter a whole lot and then only use the last bits, so they will be toggling a lot slower. So let's go to the computer and see how we do that. So obviously our counter is counting way too fast, and we need to do something about that. The signal we're counting up is this logic vector, which is a 4-bit signal. And every time it reaches 1, 1, 1, 1, it wraps around to 0 and starts all over. We could just increase this to, say, maybe 30 bits. Then it would need to increment all the way to, it should actually be 29, all the way to, then it would need to count 30 once, before it starts over, and that would of course take much longer. But now we also need to fix this, because the output is 4-bit and we're trying to assign it a 30-bit value. We cannot do that. So we take, I think we can just write output, and then we need to write what we want here. So it should be 29 down 2, and then 4 bits would give us 25, right? Let's see if this works. Oh, no, don't do that. It tells us that the JTAG chain has been modified. We don't necessarily want to save it because it's only one device, so we'll just set it up again. And yes, it tells us that this has 5 elements and it must have 4 because it should be 26. Yeah, because both are included, so it has to be, you have to subtract 1. It makes perfect sense, I just didn't pay attention. And all this analysis and synthesis, fitting, assembler, time quest, it takes a bit of time. So we'll program the device again. And now you can see our counter is definitely counting. So I think this will be it for this video. I hope it wasn't too confusing. I basically wanted to take you right from the beginning and to get something onto the board in this video. I know I skipped rather quickly across some of the topics, but we'll go into more detail with those later. And you will also see it again and again when we write the code for the clock. So that's that. I hope you enjoyed this video, and if you did, please give it the thumbs up. You're also welcome to leave comments on what you think and if we should do something differently, and of course comment on whatever you like. And just to demonstrate that the program is only in the FPGA, and the FPGA will die completely when you turn the power off. You have to reprogram them every time you power them up. So when we power it up, we will be back to the standard program. We can though flash our configuration into the flash memory so that it will load that every time it starts up. But just for testing and trying out random stuff, this is easier. Thanks for watching this video, and I will see you in the next one. See you.